Welcome all to this distinguished seminar. For many years, we all know the importance of interdisciplinary research, but quite often we end up working with people in closely related fields. Why? Because it's very hard to bridge the gap among different disciplines and integrate diverse perspectives, right? So when Professor Ma told me in the past few years, he and his team, a group of top-notch AI people, studied a lot of science. I immediately realized these are the right people who can work for AI for science. We all have the feeling that AI can do something for scientific discovery, but what AI can do, what AI cannot do for scientific discovery, we don't know. Today, we are very honored to have Professor Ma to give us a talk and share with their findings and their vision of AI for science. Professor Ma is a world-leading computer scientist, made a significant contribution to bridge the gap between academia and industry, between AI and science. Without further ado, let's welcome Professor Ma.
Okay. Yeah, it's my honor and great pleasure to be here. And thanks, Professor Jianping's invitation. And yeah, as Jianping has just mentioned, I was a computer scientist working in content generation and search engine and recommender system for almost 20 years. I was in Microsoft Research Asia for 16 years, and ByteDance for about 3.5 years. So as you can see, my background has been on traditional AI and trying to mimic human intelligence. But over the last 3-4 years, I switched my major research focus to AI for science. And there's a reason for that. And there's also rationale behind it. So today, I want to actually use this opportunity to share with you what I see for the future. And if you agree with me, because over my last 20 years of career, I always made the right bet. I made the right bet. So this time, I bet on AI, using AI to further empower scientific discovery. So the next 10 minutes, I want to first tell you what I'm going to tell you. The key message I really want to deliver today. So today, I see what's going on in AI is we are moving from human intelligence, basically trying to achieve or reproduce, realize artificial human intelligence, but further to natural intelligence. When I was working in Microsoft, the vision, the dream of Bill Gates is always like, can we make a personal computer able to see, able to speak, able to write, able to answer questions or do certain tasks? So we have been working on this. And over the last three years, and people start to notice the name called AI generative content. We start to see AI technology has been improving so fast that they can generate face image, just like real. But this is nothing today. But this is like 4 years ago, 5 years ago. And when I was in ByteDance, we have been working on technology to automatically create text. For example, can we automatically create a title for an article or write a summary of article? Because by doing this, we can actually recommend more content to the user. Can we generate advertisement automatically based on content people may want to see? So a lot of work has been going on when I was working in ByteDance in this something we call text generation. And when GPT-2 appeared and start to actually produce pretty good text. Oh, by the way, text generation is very, very hard problem because when I was working on this problem, we can generate text, but you can easily identify flaws. You know, the logic is not right, or it contradicts itself, you know, and also sometimes it's not smooth, right? So there are all kinds of problems. But today you use ChatGPT, you cannot distinguish, you know, the content written by AI from humans. And so then about 2 years ago, we have this OpenAI ChatGPT moment that people start to think generative AI is the next big thing. So today, basically what I want to say is, although you can continue working on this, today all the startup, the AI startup continue to focus on this opportunity. But because I've been in this area for more than 20 years, I said this is like Internet 4.0. There are still plenty of opportunity, but probably will be realized by those big tech or the big company in China, you know, the BAT, you know, or Huawei. But if we actually move into this area, I feel it's still wide open opportunity. It's like a blue ocean. There are still full of opportunity and things we can do, particularly in university. You know, I want to emphasize this. Today, the opportunity, if you want to work in university, academic research, I feel this is the big opportunity. So we are moving from human intelligence to natural intelligence. That's the next frontier for AI. And so today I'm going to also briefly talk about the capability, the key capability of current AI technology. Because I know there are many people in the room, probably not, their majors are not computer science. And, but hopefully after today's talk, at least intuitively, you know what AI can do. And this helps you to also know what AI cannot do. So this helps you formulate the problem in the right way. You can take advantage of the true power of AI. The first, today's AI is very good, you know, compared to human being. Very good at discovering low-level structure, low-level pattern, low-level correlations in a very high-dimensional data space. Human beings are not good at that. Usually, more than 4 dimensions, you know, you are hard to see what's going on. But today, a lot of scientific problems like a protein structure prediction, you know, that knowledge is hidden inside a high-dimensional space. But AI can find how to predict, you know, protein structure. But for the biologists, they took years, right? 2 years, even they have so much insight, they have seen so many data, but still they cannot figure out, you know, the relationship between sequence to the structure, right? So AlphaFold 2, 3 recently, really, I think it's one of the best examples. And the second insight is about deep structure. I think deep learning started in like 2012. And a lot of people now today really understand why deep structure works. Essentially, is this kind of hierarchical structure of deep neural network essentially gives you opportunity to do iterative optimization. And the second is, the third is why big model works so well. It's counterintuitive because we used to think that big model will have all kinds of problems because big model means model is bigger than data. You overfeed. You overfeed the data, then potentially it's going to hurt the generalization problem, right? The error of classification is going to decrease. Yes, indeed, that's the problem you will see from your experiment. But recently, people start to realize, if you go from training a classifier to building a generative AI, means you want to generate things it's not in your data. Things doesn't exist in the world. You need interpolation. And big data actually help you to do better interpolation. And so that's the reason it works so well when we are trying to generate data, generate NLP, generate image, generate video. So that's basically advantage of big. And the fourth thing is high quality data is very, very important. Today, actually, there's a researcher from OpenAI recently published something. I think he has a very good insight. He said that all the different models, actually, as long as your model are good enough, and you train them well, and train them with sufficient time, they are going to all converge to a pretty good place. But the data actually decide where you converge to. So now when you choose different open source model, essentially you are choosing the data behind it. So you are choosing data. So there's no like magic there. It's the distribution of data actually train the model. So, but how do you find the big high quality data with good label? It's very, very important. And the last one is scaling law. Great, today we have a scaling law. A lot of people criticize scaling law, including one of my good friends, Ima, Professor Ima, all right? But my opinion is it's actually good, just like a Moore's law. When we have Moore's law, enjoy it, but do not rest on it. Let's continue, move the technology forward. But today we have a scaling law, and scaling law is good for big tech, because you need to put a lot of computational resource, a lot of data, and for small company like startup, it's becoming harder and harder. That's the reason I'm moving to AI for science, because that's still at the early stage. So there's still a lot of opportunity we can do. Okay, the next key message, science, this endless frontier, today I think it's going to be disrupted. So that's the reason I feel I'm a little bit worried for those traditional scientists in this area. Biology, chemistry, material science, energy, medicine, because all these different sciences are going through this transformation. The first one is digital transformation. And so that's the reason we have big data. And we also see lab automation, because for this field, typically you have wet lab. You still need to do certain experiments to verify. But even that is now being automated by this high throughput automatic experiment like a robot in the lab. You see that now in many biological labs. And AI for science is providing more power, more resource into this area. And this is the slide I'm going to tell you today. Because a lot of people told me that AI for science is not new. There are many professors has been working in this area. But I have to say that their strategy is mostly based on computation. Computational biology, based on a lot of prior knowledge to design the AI with inductive bias, so that make them very complicated. So when you have a big data, they may not be able to scale easily. So that's the reason I feel right now the model is simple and they use a lot of data to train it. So that's the reason I feel these are new. These 6 things are new. First is generative AI and large language model were not there when those computational scientists are working on all kinds of things for like a biology, chemistry, material science. And I also feel now is opportunity to see if we can build foundation model, which is multi-model, multi-agent, pre-trained, but for each field, and also the major application, like a drug discovery. Can we build one by bringing all the data from all the big farmers, and then really create this foundation model for mankind? And the third one is wet lab, dry lab. Now it's also being closed, this feedback loop. And also, I think at the beginning, we are going to see more AI copilot for scientists instead of completely automate everything, because this allows us to continue, accumulate more data, and also the other one. And the last one is based on, the big data we can actually create it for each field, and also the scientific literature and knowledge. We can actually build something called autonomous AI, and I'm also going to briefly talk about it at the end of my talk. Okay, so because of all this, I also feel for university education and research, it's time to think about how we are going to train the next generation talent. And also, instead of, I think we can actually play a more leading role and to lead many industry development. Yeah, so there's also a lot of opportunity there. Okay. So this is almost like the conclusion of my talk. Basically, at this new era of scientific discovery powered by AI, I feel we need to actually build a foundation. This layer includes all the latest algorithm, tool, and also computing resource, those infrastructure to support the development of AI, but to empower different research fields and deeply integrate with different disciplines. But on the top, really using a lot of new innovation, collaboration with industry partners, and incubate our new startup to drive, using this as a need and the value creation process to drive our research and also education. Yeah, so this also this is part of my the purpose of my trip, is really to find a way to collaborate with CTU, and particularly with Jianping and many other professors, Lu Jian and also Alex Ren, and many actually professors in CTU who are so strong in science area. And I believe by working together, we can shape the future of science. And by bringing this together, So I'm currently in the stage of thinking about how we build new type of organization, to bring both top AI scientists, and also top scientists in biology, chemistry, material science together, and also bring industrial partners and also other academia collaborators together, and really build this center together so we can continue to drive the innovation. Okay, so basically this is my first set of slides. It's essentially the key message I want to deliver from today's talk. Okay, for the rest of the talk, I'm going to touch each topic gradually. I want to talk about generative AI and large language model, and briefly introduce how the history of the development in this area. And the second, talk about AI for science. And the third, I'm going to show you many recent application and development, and also future direction. Okay, first, on generative AI and large language model. I already kind of show you this slide because, first of all, because I have been working on these two areas for pretty much 20 years. And when I saw this area, some natural language NLP researchers started to work on molecule generation. This was 2019, before the pandemic. Then I was curious why NLP people, those people working on text, are working on drug discovery at that time. I was very, very curious because it's so irrelevant, right? Then I asked one of my team members to do a survey. After I saw what they are working on, I immediately realized, wow, this is the next big thing, particularly for NLP people. So my background, you can think of me as a people working on search engine recommender system and the text generation for so many years. And I saw this. Then I said, oh, we can definitely do something much, much better than all the existing technology and research. And this is a conversational AI, and people are already using. This is basically an example, assuming like you are president of Tsinghua University, and I'm his secretary. I was tasked to write a script, to welcome the new student, and automatically, generate an article for you with your prompt. Although you need to provide a prompt, But I have to say that when I saw this, I feel it's better than me. I cannot actually write this. So right now, a lot of those paperwork done by my secretary, actually, she used ChatGPT. I also now use ChatGPT to almost to do all the English editing. They do it so well. So a lot of tasks has been being actually conducted by ChatGPT-like service. And a little bit on the content creation, because as I mentioned, I worked in ByteDance before. I want to show you during those 3 years what we try to do. Today, let me show you the first one. It's a video generation.
小时候真傻，居然盼着长大。想回到过去，试着让故事继续。
This was a video generation, but it's basically trying to make you older and younger, but have to look similar to you. It's not someone else. It's actually not easy, but this was done by GAN, Adversary Network. And the second one, okay.
嘿，宝贝，来了。月亮不睡，你不睡，你是秃头小宝贝，勾天不端奶茶杯，孤苦一生无人追，了不起了不起。
Okay.
抖音。
And this is the music generation. We also try to actually build a feature for user to automatically create music based on your video. So the rhythm but the music is automatic. But now it actually does much better job. This was like 4 years ago. Yeah. And one more. Big one. Okay, so this was 4 years ago. And this year, when I saw Sora, what they have been able to do, let me show you. The first video is actually, they have a multi-model video generation from text. You give this generator a text script, it will create a video actually according to what your text description. And let me show you the first example. Oh, they haven't put music yet, but I feel it would be nice, to also include music. So as you can see, they actually, almost you can see the reflection, right, from the water on the ground. Quite real. But if you look at the lake here, there will be some problem there if you look very closely. It's not completely correct yet. But overall, you see it's already, pretty good. Yeah. And this is another one. You can generate a movie trailer easily, but this is also based on the text description. Think about people use this to create a movie easily, right? So I think this is going to disrupt Hollywood and also the movie industry. And of course, I tell my colleague in ByteDance, Douyin, TikTok need to actually, basically integrate this technology, or 剪映, you probably know what I'm talking about, the video editor. I think this will be super powerful, for those kind of tools. And you can actually do many very interesting things like connecting these two videos. This is one video. The other video, butterfly. You want to change that drone into a butterfly. You can start to, use the technology to create all kinds of special effects. Okay, so you have seen what generative AI can do today for video generation, and let's take a step back and answer the question, what is intelligence? How to achieve it? AI has been through, I think if we look at like more than 40 years, it has been through many stages, and there's an upturn and downturn. There's like a winter, at least 3 winters over the past like 40 years. And there are many methods has been tried in the past. But today I'm going to just tell you one method which really dominates today. It's neural networks. Of course, inspired by human brain. I just want to give you a scale, to understand the size. In the typical human brain, there are 86 billion neurons. 86 billion neurons. And each neuron is connected to about 10,000 other neurons. And through the approximately 1,000 trillion synapses. So that's the connection, And also, if you think about the universe, it's also like a neural network, and there's an interaction between stars, right? And we don't quite know what kind of interaction. But if you look at the scale, they have about 20 to 40 billions of stars. So sometimes if you do a network, create a pretty big neural network, and they are going to give you an interesting opportunity. Okay, but a lot of people don't know why neural network work. I want to quickly introduce some. let's take one example, okay? So let's say you want to learn a classifier. There's two types of data. One is dog image, the other is cat image. And you want computer or neural network to learn, that a new sample come in. You want to tell whether or not it's cat or dog. And one simple thing is to actually identify this decision boundary to separate these two spaces into two. One is belong to dog, the other belong to cat, and you are done. And essentially, this is equivalent to what each neuron, one single neuron can do. Each neuron is essentially represent one hyperplane in a high-dimensional space to cut it in half. So that's each neuron can do, okay? So separate the whole space into two, so you can do encoding. Anything fall into here, you can encode 1, the other 0. So it's about encoding and decoding, compression and decompression. I want to basically lead you to there, okay? So each neuron is a hyperplane, okay? So, but you need to do parameter tuning, the W1, W2 decide, where this hyperplane is. Of course, you can put it there, or move it here, or there, or rotate. This basically determined by your parameter. Okay, so you need to learn. You need to use data to learn, where to put it. Okay, so if you can learn correctly, you can get a discriminator model pretty good. Okay, you are done. But the problem is most data are not that simple. Let's say you have two types of data, cat and dog, and this is their real distribution in the original representation space, original data. Then it's pretty complicated, and you have another new data coming. You try to decide whether or not they are red or blue. It's becoming non-trivial. But again, it actually can be done. Let's do it. Adding more dimension. It's still one neuron represent one cut of this space. And I can add in 2 second neuron to cut the space again. I can add more. So I'm doing encoding. I'm partitioning the space, original representation space, into subspace. So the output of each neuron essentially tell me where those data is in the original space. And it's encoding. Think about the output of this 4 neurons, 01, 01, 01, 01, give you a unique encoding of the original data representation in the original data representation space. And this is called encoding, okay? So each neuron can encode the data in such a way. Then I can easily add one more neuron. Think about I increase the dimension of the data. Of course, I need to add a hidden neural layer. I can actually give 1 to dog, -1 or 0 to cat. I can easily separate this data by adding one more dimension. Think about I just adding one more dimension as the output of neuron. And I can manipulate any data, no matter how complicated they are. I can make them separable, perfectly separable. So just think about this, okay. Then I can actually transform the data to a new representation space. And that can be easily done by adding one more neuron to separate this space. So this is essentially how classifier work. But today, a lot of generative model, they need to learn a probability. Instead of just finding the boundary here, we want to learn these two distributions. So you can sample, for example, I come here to just sample any data. It will look like a dog. Any data here, I just sample it. It will look like cat, all kinds of cat. And if I sample something here, it will be something look like more like a dog and cat combined. So that's the power. So, but essentially, neural network is the way to encode the representation from one space and to the other, and trying to learn how to compress the data into low-level structure. They can be recovered, decompressed. They can decompress again. Then it's an image, but it's not traditional compression, decompression. It's semantically you can decompress and compress and decompress. You can interactively, just like you put a different prompt, it's going to give you a different answer. So that is not easy. So So every time Emma says, this is a compression, decompression, I say, not that simple. It's not just about trying to reduce the reconstruction error. You need to do it semantically, interactively. That's powerful intelligence. And so I think, but overall, you know how neural network learn and can be trained. Okay, so starting from 2012, and neural networks start to go deep. Now this is an AlexNet, and it's 8 layers, but it can be used to do handwriting recognition pretty well. And from 2012 to 2016, is the period of time that neural networks start to grow deeper and deeper. Many of you probably already, this 10 years ago, probably completely forgotten. But like a ResNet, was the deepest neural network at that time. So think about every time I add in one more layer, what can I do? I can partition the space further, no matter how hard it is. I just add in more layer. And every time I encode, decode, and the nonlinear transform, and use all attention, right? And you can use this to solve any problem. So wonderful. And so starting from 16 to 24, that's the period of time that neural networks start to grow bigger. I just want to show you the size of parameter. Like a GPT-2 was 1.5 billion, and GPT-3 was already 175 billion. So the comparison is this one to this one. And compared to GPT-4, because I cannot use that chart, it's completely off. So it's like this is Earth, this is Sun. That's how quickly the size, the number of parameters has grown. And the nice probability of big model is they actually show some amazing capability. This chart basically shows you that when you add more data and more parameter, yeah, the model continue to improve. But you will expect they improve like linearly or proportional to your data or the size of your parameter. But just interesting things at a certain point, it just improves so quickly, becomes so powerful. I think this maybe explain you have the size of brain like a fly and a human being, right? Our intelligence level is so much bigger than the brain, the size of brain for the fly. But this is just one analogy, But people don't know why, just at a certain point they just continue, just improve so quickly. So they call this emergent ability. But your model need to reach to certain size. Sometimes you don't know where they are. Maybe we are here for several years, but certainly reach to this point, you are going to see significant improvement. And there are also many people ask why big model work. I already briefly explained. There's an effect called double descent. And this is a classical regime, which is you don't want your model to act at least smaller than your data, right? That's reasonable. So you don't over-parameterize. And so we have been in this space for years, 20 years. No one dared to go here, because people believe it's going to get worse. Yeah, indeed, it gets worse. But we never reach to this ratio. This ratio is model size equal to data size. Means, think about this, means your model is going to pass all the data, trying to fit all the data you have. Then you will say, yeah, you are going to overfit your data, and it's going to hurt your generalization capability. Indeed hurt. But the problem is, once you reach to that ratio, and they go into this new interpolation regime, and this is over-parameterized. But it's good for generative AI. When you're trying to create things, that space is what we want to go to. So this is just show you, this is OpenAI Sora. You already seen the example. But they show this like a stable scale. This is base layer. Okay? Let me see. You have a base compute and 4 times, and also 22 times. And you can see the significant improvement, right? Let me show you once. The first is real animal. But to the right, you see it's nailed. It nailed the content. Yeah. So this is actually just highlight how important the high quality data is, and also using scaling law. And this is the scaling law. Basically in NLP, and these different colors show you the different number of parameters, the different scale. And as you can see, when the scale go bigger, and they actually converge quicker, they also continue to improve. And the similar effect also we can see from protein language model as well. So, but we don't know how long this scaling law will exist. I don't know. Maybe we'll continue for several years. We can benefit from scaling law, maybe until a certain point. Maybe it cannot give a further improvement. It's possible. But at this stage, we don't know how long this is going to last. But it's a good thing. And briefly about generative AI. One easy way to think about GPT is something like this. That we can actually formulate the problem. Let me tell you, any generative AI, the goal is to bring these two distributions closer. The first distribution is data distribution. Assuming you have all the data you need, for example, all the human face in the world, including the past and the future. And if you have this data set, you are done, right? You can go there, just sample any data, and it's going to look like a face, someone's face. But the problem is it's impossible to get all the data. Okay, so what we do is we're trying to create a model called setup. And this model, if this model distribution is closer to the data distribution, and you can go there to sample, and any sample you get out, it's going to similar to what you do in this original data space. So we are learning from data to create a model with parameters that can approximate this distribution. Okay, so this is GPT, means once you have the first word, I can use that to predict the second word. And once I have the first and second word, I can use the two words to predict the third. And I can continue to do this 1, 2, 3, and predict 4. And ChatGPT at the beginning, they can predict like 10,000. Now it's probably huge token space. Now you can probably to 1 million token space. And so means GPT today can read a whole book about you and predict the next one. So it's become personalized. It can answer whatever the question about you or someone or some field. So that's the scale has reached. But fundamentally, it's like a probability prediction, predict the next word. And the nice thing is that today, all the major AI is but essentially easy to parameterize them by transformer. So you don't need to create new things. You just use transformer to parameterize. So it becomes also quite engineering. Okay, so auto-regressive model for text generation used to be there are two different methods. One is, as I mentioned, GPT is predict the next word. So from left to right, easy. So I think it's actually easy to understand. There's another model which used to be very popular as well. It's called bidirectional encoder representation from transformer. Means you have a two word and predict something in between. So you will easily assume the second one should work better than the first one. Yeah, it actually works better, but it's hard to scale. So simple things, GPT now become more dominant, but it's predict from the left to right instead of bidirectional. Okay, so there are actually many different approaches for generative AI. I just talked about GPT, which belongs to auto-regressive model, but there are also many other versions, like a variational autoencoder or GAN and diffusion. There are many different ways you can model the probability, but the goal is the same, to bring these two distributions closer. But you can try different model. And nice things, you just parameterize by transformer. So it's very, very easy today. This is almost like a methodology. I give it to you. Everything is pretty much here for the existing AI, like image generation or NLP generation. That's pretty much it. So the diffusion model for image generation work like this. They're basically trying to learn, an image generation from white noise to something meaningful. So given the image, they will learn how to, by adding more noise and gradually degrade the image, to noise, and then learn how to go backward and forward. So you will learn the path. And although in order to do it right, stably, it's very hard. But essentially, you change a distribution from white noise to something else. So that's diffusion. And Sora, although look like a miracle, the model is actually not new. It's essentially something called scalable diffusion model with transformer. They basically do it in a very, very aggressive large scale. Means every frame is going to encode each frame into like a tensor. And they are going to actually learn how to, by adding noise, turn it into a white noise and clear again. So how to train this is hard. But essentially, the model is actually pretty there. It's not something new. It's also based on diffusion. But the amazing effect. Okay, so here just to summarize again, to understand current AI technology, essentially, this is the 5 most important message or lesson you can learn, from all the things we have been doing over the last 10 years. You know why we go deep and then go big. And data is important and scaling law is here. Okay, now let me move on to AI for science. Okay, so the GPT has been applied to science already over the last 3 years. Even GPT, general GPT has been growing, but the same for science. People are applying GPT, for example, for vertical domain, like building a biomed GTP, a large language for biomedicine. Or people even building a chat doctor, like a special chatbot you can talk to is like a doctor. They can also pass some medical exam, better than human being now. Human doctor, they can do better on the exam. But whether or not you're going to trust him is another issue. But people has been doing that. And there's also using ChatGPT for molecular data, protein data. This has been also going on. Yeah, so I just want to mention this is a very active research area. And, but naturally, I think from people who has been working on natural language processing generation for so many years, I easily see the problem in this way. Protein is like a foreign language. Think about protein as a sequence, right? Then, although they fall into certain 3D structure. But you can think about this sequence with 20 different kind of amino acids. It's a foreign language we just don't understand. We cannot read, we cannot write. But that's okay, but AI can read and write, then that's good enough. So, but we can formulate the same way, right? If you look at NLP, people has been working on, for example, from word level, right? And also sentence, paragraph, and also meaning, all kinds of like semantic parser, all kinds of things. But nowadays, NLP is very easy. You completely just ignore all the former technology and go to data-driven approach. But you can have this analogy of these two data, right? Protein and language. So semantic parsing is like a protein structure prediction. Very similar. And generate text is very similar to generate protein. If we can generate protein, think about that. That's incredible, right? So people has been trying this. Okay, so this is like an image generation, as I mentioned, and they use similar technology for protein generation. This is a protein from randomly position all the amino acids and small molecule, and you want to learn gradually, from random to something with structure. People has been applying this as well. But our perspective is actually create this field by using this new approach. It's similar to from bits to atoms. can we create a generative AI, but we are not using word or pixel, but we use atom to compose new protein or new material or new chemistry, chemical compound, because they are similar. They are all simple. So this is the area right now we are working on called complex symbiotic system. But it's perfectly positioned for AI, for science. And how we do it? All the molecule system, you basically, you can only, each symbol come from this table. And there's also protein system and also genetic system. And so we want to apply, what we have done in NLP into this space. So one of the models we have been working on is called geometric graph generation. If we can actually represent all the different data, all the different applications into this unified problem, unified representation called geometric graph. And if we can handle the generation of this graph based on certain property or certain 3D structure we want and certain constraint, and we will be able to apply to all the different tasks, like a protein design will be equivalent to generate a large graph. And structure-based drug design will be equivalent to conditional geometric graph generation, given certain constraint and you generate that graph. And catalyst system, it will be equivalent to geometric graph generation plus periodic metric generation, gives additional different type of constraint. And we can actually unify all the problem here, all the application here into the same methodology. And that's what we want to do. But in order to do that, there are actually many new challenges compared to generate image, generate text. And I am going to talk about each challenge separately. The first one is there's no intrinsic order in, for example, in molecule or protein. For the text, you can say from left to right. But for the molecule and protein, it's hard to say where we should begin the prediction. Given this first and then predict the next, but it will not be the best order, right? Essentially, this type of data, there's no order. There's no intrinsic order. So that's the reason when you try to apply GPT auto-regressive type of model into this space, it's not perfect fit. There are many, many problems and limitations. And then how about diffusion? For the image, right, you gradually adding noise. And so from the coarse to fine, essentially also give you some order. But probably in the molecule and protein space, they have a certain structural constraint. If you actually change the distance of these two molecules, for example, this Qing, I forgot that, then it's not stable. You cannot easily just change the coordinate of each atom. So because there's a structural constraint. So this adding noise through diffusion model, there's also certain limitation. And the third challenge is, by default, we need to handle both continuous and discrete representation. Single NLP is discrete. Image and video is continuous data. But the molecule, essentially coordinate variable is continuous. But the type of atoms, like for this location, and what type of atom they are, is discrete. Discrete data, there's a problem for discrete data. It's hard to measure the distance. Continuous data, you can easily measure distance, but not for discrete data, not for NLP, right? So that's the reason, by default, handle this type of problem, you need multi-model AI to learn the representation. And the fourth one is geometric symmetry. We want to make sure the learn probability density function is roto-translational invariant, because in the 3D space, they can change the rotation. You don't want your representation learning affected by this kind of symmetry problem. And this becomes very hard. It's not like image or text. But somehow we nail this problem. Okay, so this is a paper we published at Neuro IPS, and it was an oral presentation. And this paper actually received a lot of attention. It's called GeoBFN. BFN means Bayesian Flow Network. It's a new type of generative model, particularly good for the problem I just mentioned and for the challenges we are facing. But we need to extend this for geometric graph. So this paper has been published, and essentially we handle the problem, the challenge I mentioned, and by combining autoregressive model with latent variable like a large language model, but jointly model all dimension like a diffusion model. But this is detail. But we can handle these three challenges in the same unified model. And this model turned out to be so much powerful than diffusion-based method. Let me show you. This is 3D generation based on diffusion. As you can see, it's not quite stable. Suddenly, at the beginning, you see it's jumping around. Essentially, it's not quite stable until, finally, suddenly it becomes, But you can see from GeoBFN, it actually converges much, much smoothly. And they find the right position, the coordinate, and the type of atom much, much quickly. And there are two papers we published to talk about how to do that. And this is some result, and show you compare with all the existing diffusion generative AI method, and we outperform. These are the other approach. And they also need to decide how many steps. We can actually adapt based on how much time you have to train, and we'll continue to improve. And the speed of convergence is 20 times better than all the existing methods. Okay, 10 more minutes. Quickly, I want to talk about application. The first area we pick up to apply this generative AI is drug discovery and development. And the reason why we want to do that, although it's not easy, later I realized, wow, there are still so many problems. But when I look at the traditional farmer, big farmer, it actually takes so long, more than 10 years, and also huge investment, 2.5 billion, to develop just one single new drug. And this drug is called average drug. Everybody eat the same drug. This should not be right? We talk about precision medicine and personalized drug. But today, we are not there. So think about how hard it is, right? You have so many possible candidates, so many targets you want to find from hit to lead and do some clinical trial, and you go to phase 1, 2, 3. It's 10 years, more than 10 years. One drug, huge investment, right? Can AI do better? I believe so. So I picked this area first. And one thing we have done is we look into this virtual screening problem. Virtual screening is essentially the problem is like this. When you have a protein, you know the target, the space, like you want to, you want to fit a small molecule. And the problem is how can you identify this one? And there's actually a database of small molecule provided by different providers. All the red ones are commercial ones, but they are proprietary. They don't give it to you. So that's the important assets of those big pharma. They have this huge database like this one, GSK 2020. They have the size of their small molecule at this order. These are like open data set. Everyone can actually get it. But the problem is, if you want to actually identify potential drug from this huge database, you need to do virtual screening. And the bigger your size, the size of database, it took longer, right, to find it. And also, but the bigger data space, the better opportunity you are going to identify the right drug. So there's a dilemma there, right? But the problem essentially very similar to key and lock. You have a lock, 3D structure, and you want to design a key that can actually turn on that lock. So it's ligand and protein. And this, how do you these two combine together? So it's essentially this representation of solving this problem. If you can solve this problem, you are going to solve many, many problems in life science, in the protein-protein interaction. So it's a very powerful a problem if you can solve the representation of these two. How do you match? And this is called virtual screening. So now what we want to do is, can we actually learn all the target we know today and try to find key for them? Today, there's probably thousands of targets, known targets. And there are more, but today, human scientists only handle about thousands of them. Then what we want to do is identify all the key. then people can further decide how to use the key, and that's the next stage of problem. And we developed this something called drug clip. It's AI-powered virtual screening. The idea is using OpenAI clip. Essentially, this idea has been applied to connect text and image. And then now we use this to connect target and also the small molecule, right? Straightforward. But how powerful this is, this is some of the existing product, commercial product, like Schrödinger, and also some of the this is one of the startups in China. But they can only do the virtual screening at this level. Now we can go to this level now. So we can search a much, much bigger space now. So this is another comparison. So basically, given the same computing resource, like 120 CPU and 8 GPU, we want to benchmark our method with other existing technology, and that's what they can screen over a day. In a day, they can screen 20 million, 60 million to 320 million. What we can do? We can do 310 trillion. So we are going to apply this for drug discovery. Yeah. So this is still in progress. Yeah. And the second one is instead of using search to identify the molecule from an existing database, we want to generate de novo molecule. Means it doesn't exist in the database. Can we generate? And we apply this first to the structure-based drug discovery. So this will give you an idea. So essentially, you have a protein, and you know the target, the pocket, and you want to actually identify or learn a small molecule that you can actually plug into that pocket and maybe block the function or do something about it. And we can formulate a problem in this way. And we have been doing this for over the last 3 years and published many papers. They are also pretty interesting to look at. Yeah. But the problem with AI-generated drug tend to be hard to synthesize. So another way to solve this problem this is also a very clever problem. We generate a molecule directly from the synthesized tree. There's actually a tree represent how you can synthesize all kinds of chemical compounds. It's a huge tree as well. And we directly learn representation from that tree to generate something that can fit into this pocket. So anything we generate is going to be able to synthesize. So that's clever, right? So we don't go out of this space. We directly learn from this space. And that's actually quite interesting. So there's also a professor from MIT. And I think these are two top groups working on this problem. Personally, I feel this is actually trying to address the problem of how we can synthesize AI-generated drug. We also look into this protein-protein interaction and docking problem. And the first product we have been doing is this antibody design. Antibody is actually one of the most important protein, I would say, for drug. Right now, for our human body, it usually takes 7 days to evolve your adaptive immune system to produce the antibody that can bind the antigen. So it takes 7 days, for your immune system. Then my question, can we use computational approach to generate that in real time? Given an antigen, like a COVID-19, real time compute this antibody is like Y, but the most important area is here. There are about 20 amino acids. You can change the position to change the structure. And also the property of the surface allow you to bind the antigen. So basically, this area is very important, but mostly learned through your immune system, right? Try and error, 7 days. But if we can do this computationally in real time, think about that. So this is going to revolutionize what I would say this is something called the third human immune system. It's outside your body, but we can compute in real time. And they can also, once you design this antibody, there's also technology you can synthesize it. So the technology there. So it's almost like you can develop a new type of drug, antibody, for any type of new antigen or like based on, for example, for cancer. This is also one way to cure the cancer as well for the T cell. And the one work we have done is actually to create end-to-end generation. Think, you know AlphaFold. AlphaFold is given a sequence, you predict the 3D structure. And from this antigen, we predict the 3D structure antibody. And you have 3D structure antibody, you go back to know, try to identify the sequence. But we can do this end-to-end. We skip the structure prediction and also this feeding, binding problem directly from sequence to sequence. Given the sequence of antigen, we generate sequence of antibody. Think about that. Yeah, this is also very exciting work. So recently, I think protein pre-training has been a work that attract many attention, right? Science published these 3 different work. DeepMind has AlphaFold. David Baker's group from UW has a Rosetta 4. And Meta used to have an ESM, but they dissolved this group for some reason. But I feel this work is actually quite interesting because they are all focused on structure. This is basically go directly to sequence. So they can build a large language model for protein sequence. But they stopped the work. But recently, my team picked up that work. We create a new ESM. But AA means all atom. Means we directly go to the atom level. We skip the amino acid level. Because I think once you use amino acid level, sometimes give you advantage, but also constraint in terms of what things you can learn. So now we can go directly to the atom. And next stage is go to the electron. So go to the most fundamental data layer. So skip all the things in between. But this is new. This is just published recently in the HKIAS conference. And this work has been has attracted many attention because people believe this is the third way of doing things, really data-driven and go all the way to the atom scale level for the protein pre-training. The reason why we want to do that, because we want to unify all the molecule generation tasks in one model. In the past, we separate like a small molecule, big molecule, or protein, or even like a biology, chemistry, or material science are separate. My dream is to unify that. Right now, we already unify, at least for this application, molecule 3D structure prediction, protein molecule docking problem, protein peptide docking, and the peptide design, and target-based drug design, and also PROTACs drug design. All these 6 different tasks, now we are unifying them into one task. And we will also want to provide prompt engineering capability. Simple, people has been playing ChatGPT with prompt engineering here. Anyone doing prompt engineering? Okay, some of them. Yeah, doing prompt engineering for text generation. It's very interesting, right? Think about how about we can do prompt engineering for molecule generation? How do you create a prompt at the atom level? Scientists may want to explore, maybe this area, I want to do certain things, then you will focus on this area to generate certain things. So that prompt engineering capability is not available yet for all the large language model for protein or small molecule generation, but we want to do that. This is the first step. Once we unify them, all the different tasks can be done in a single model. So that would be wonderful. Yeah. And how we do that? Okay, so although it's very complicated, but I would just want to say it's actually quite simple. We're just trying to denoise, adding noise and denoise and use all kinds of data we have and try to keep the model simple. As I mentioned, don't make your model too complicated, but train them well with high quality data. So this paper is now being submitted, to some of the natural science journal. Yeah, so this is called Pocket X mode. And we actually benchmark this with AlphaFold 3 and just show you the comparison. AlphaFold 3 can only perform structure prediction, but we can support all kinds of molecule structure prediction and design because we unify the representation. And AlphaFold only support like 6 different tasks, but we want to provide prompt engineering, allow new type of tasks or more flexible way of designing the molecule or protein into the system, And there's also many other advantages. Okay, so this is what we want to do. We want to create the first generative protein foundation model in the world. And for all kind of task application. And of course, we also interested in material generation. But so far, we just started this area. But I believe a lot of our technology and work can be applied to material generation as well. And these are the 3 different type of material we are currently looking at. And we look at OLED and lipid, and this is something called, this is 钙钛矿, but perovskite, yeah, 钙钛矿, yeah, we talk about this today during the lunch. And I believe this is also interesting area that we can bring a lot of innovation into this space. Although we have been working on biology, chemistry for most of the last 3 years, but I feel this is also quite exciting. What we have done for OLED, a lot of LED screen, like this one, they need certain chemical compound to actually emit the light based on the energy. But most of the material are currently copyrighted by Samsung. Samsung owns the majority of OLED in the world. So even in China, we manufacture a lot of this monitor, but all the major IP, are from Samsung. And then our question, can we identify new OLED molecule, through AI? But those molecules need to be optimized for these 3 properties. And we also recently actually achieved some very interesting results with some of the professors in Tsinghua University as a joint research project. And quickly, we are also exploring how we can close the feedback loop. Here is using AI to design experiment. Because AI can really see the data distribution, it will know not only the positive example. AI sometimes also want to do experiment on the negative sample so that they can collect more data to train the classify or generate model. So currently, the scientists will only try things they believe they are going to work. If they know this is going to fail, they will not do it. But for AI want to fail as well, because those failures can help them to learn. But if AI can actually see a much, much bigger space and also what data are needed, and they can guide the experimental design and use automation, robotic to actually produce the result and get the data, big data back, think about we close this loop. That would be amazing. And the next one, although I haven't talked about much today, my team also work on something called biomedical GPT. It's trained based on knowledge graph and also literature. I truly believe today we need a new Google Scholar, need a new Microsoft Academic Search, because I used to work on Microsoft Academic Search. Think about if we can turn Google Scholar or Academic Search into something more like a ChatGPT, but for scientific discovery. You can ask all kinds of interesting open questions. Then read all the scientific literature and give you the answer, and you can interact. And also the representation itself will also learn from some molecule data, many other different modality data. And then we augment this AI for science with scientific literature and knowledge. Actually, someone came to me to discuss the possibility of doing this as well in China. Yeah, I would say let's bring all the knowledge and literature into this space as well. And last one, this is recently there are many GPT used to integrate with many external tools. I believe this can also be done for scientific discovery. And this is someone actually from chemistry field did something like this. They basically create a GPT, but integrating 13 different expert design tools. This can be external tool, but you teach AI to actually use it and then close the loop. So this actually helps the scientists to discover many new chemical compound and new capability emerge as well. And if we include both knowledge and scientific literature and also external tool and also all the knowledge we can learn from molecule data, protein data, and I feel we are almost there. Think about AI can explore science automatically. And this is the future. Yeah. So here I just want to summarize again, because This is something you probably know why I'm talking about autonomous AI for scientific exploration and discovery. Okay. Yeah, so lastly, I want to give a new definition for science. Although this is I need to do this very careful, you know. But I believe this may be the time we can redefine science because of this new methodology and tool we have. This is the definition of all science. This is from dictionary. Systematic endeavor that builds and organizes knowledge in the form of testable explanation and prediction about the universe. Okay, this is old definition. And what's the new definition? Yeah, I want to add, this is the same, okay, pretty much the same. But instead of organized knowledge, I would say knowledge is something that you can explain, right? A lot of people talk about we should build explainable AI. I think no. Why you need the AI to be explainable? Because the big model, the high dimensional space, sometimes people cannot understand, but AI can understand. So we just need to include models into this knowledge we are trying to organize. And also allow this to be useful for both non-human beings and also AI, and they can cooperate in a new way. So because AI is good, I would say AI is actually much better than human at understanding and generating, I would say even including generating very high dimensional data and learning the pattern, structural relationship, correlation, between them. AI is actually better than human being in this space. But the problem is that such knowledge and model are often beyond human comprehension, right? So we should not limit, we should not constrain what AI can do, So I feel we even need to think about at some point we put AI first, even first, not always, not just be a tool used by human. AI can be first, and everything we try to organize here can be of AI, by AI for AI. Although it's controversial, but I want to make a very strong point, to really this out-of-box thinking, because we want to. That's the reason we want to systematically build up different type of foundation model for scientific discovery. And at the beginning, I talk about AI should move from just mimicking human intelligence to natural intelligences. This will unleash our imagination. If we just trying to mimic human intelligence, AI itself can be a science. That's many people talk about not AI for science, but AI as a science means beyond human intelligence, like this learn how this incredible intelligent universe is doing to create all kinds of life, all kinds of protein, all kinds of material. That's actually principle behind it, but just we don't quite nail it yet. I believe with this new powerful technology and tool, we can actually do more in science space as well. Okay, so this is also the end of my talk. I want to mention again, my purpose here to deliver this lecture is really to find an opportunity we can collaborate. I personally believe this is the next big thing for the next 10 to 20 years. I believe something big is going to appear, and much bigger than Internet 4.0. Much better than today's AI application, still on image, text, video, music, speech, although they are still good, but if we can disrupt science, we create a lot of industrial development opportunity as well. Okay, so this is again another slide showing in terms of methodology, how we can do it, from bottom to top. Okay, yeah, so lastly, I want to acknowledge the work actually done by my team. All right, this is in Chinese, but I have a pretty strong team. I'm really proud of them, and they are so good. Without them, I cannot actually do all the work and deliver this lecture here. Okay, okay, thank you. I will stop here and take questions.
This is definitely the most inspiring talk I have ever attended. So now we open the floor for questions. Maybe I start with Shuai. This is he's doing for bioinformatics.
Yeah, I think it's a very exciting talk, and thank you. So I'm curious about how can you model the proteins into graphs? And also DNA is a very large molecular. And do you want to model that use hierarchical models, or you just have some other things?
Yeah, that's really called geometric graph. No, it's not typical like a 2D or 3D graph. Yeah. So we're basically trying to model each pairwise relationship. So we use a huge. I would say I can actually go to that slide. But anyway, you can actually turn the representation into a geometric graph. It's one by one. It's complete representation, and then you learn from there to learn a generating model. Yeah. So this is called GGG. If you can do generation of GGG, then you can apply to graphics as well. I feel a lot of area also can be benefited by this new capability. Yeah. It's one by one. It's one-to-one mapping. We can create that one-to-one mapping. Yeah. Without loss any information.
Okay. Yeah. Thank you.
We are.
Professor Mai, thank you for your informative talk. I'm Yang from some engineering and also materials. I've been using AI for quite some time to design new metals and alloys. And after listening to your talk, I understand what you mean by AI for science. So here's I want to seek your take on this issue. In this field, people have been using VAE GAN model to generate materials and to study the properties. But we never take it as a science, because by science we mean that understanding the mechanism, the physics, right? That's what science means. But for AI, it's for us like a black box. It is so complicated, but it can provide something really useful. We can get the solution without understanding why. That's something we like AI. But when it comes to science, it's not that science at all. It's engineering. It's a tool that bypassing many obstacles, because of the complexities of the underlying science. I think that's also the criticism of the many colleagues in the field. They never said that, okay, so never use AI in that straightforward way. You must explain why you can achieve these good results. I think we want to secure feedback on this, the first one. The second one is, when you look at all these applications, there's one fundamental assumption that the data is sufficiently large. You don't worry about data, right? All quality data. But back to the specific areas of material science, that's the luxuries you have, but we don't have that one. Usually the data is quite small. So we have a tendency to reduce the size of the data to make, to have fewer data descriptors in order to fit into the small data size. So, but it turns out that, okay, it works fine, even though you don't have large data. So do you encounter similar kind of problem? You don't have to fit in large data, but it's still with a small size, the model that can achieve the good results. I'm wondering why that's the case. Okay, maybe that's something science want to find out. Okay, thank you. That's the two questions I want to raise at the moment. Thank you.
Yeah, thank you. Very, very good question. Yeah, I feel that's reason I think for some foreseeable future, a certain period of time, I feel AI and science is going to collaborate instead of AI automate everything. Although I feel in the long term, AI could potentially become so powerful, that can actually do a lot of things beyond than guided by scientists as a tool only. Yeah, but I think at the beginning, what we want to build is something more like a copilot, like an AI copilot for scientists. And that's the reason there's another word we did. We build this interactive drug design tool. So you can almost like have a conversation with the AI drug designer. But the human scientists are actually using that, to have a conversation, interaction, and provide feedback, and tell them whether or not they are doing good or bad or right or wrong. And so I think this kind of interaction, like a human-computer interaction, HCI, we also need that in this space. But right now, I think we don't build a tool in this way yet. But I feel probably we need to take this approach at the beginning, allow scientists use AI quicker and also on their task first, and we can collect more data and learn from that. And so I feel eventually, I think short term and the long term, I think we just probably do it differently. And also short term wise, there are small data problems. Many areas actually they don't have sufficient data. This reason right now when I try to talk to different people in this field, the one thing I look at, do you have data? A lot of I have to say that after the discussion, I realized they have only very small data because they do all the manual, lab experiment to collect certain data, which is so precious to them. They don't want to share with you. I have to say that. A lot of particular biologists, the data is their life, but their data is not big. I have to say that it's not big enough. And for the power of the current AI to really, exhibit the true capability. So I think there's a period of time we are going to use a lot of human knowledge prior, bring a lot of inductive bias into the model, and that's okay too. So a lot of AI for science paper essentially is about bringing a lot of those first principle, a lot of human knowledge into the design of the model, but which also make the model is very complicated, not easy to scale. But they are going to, they work for some period of time. But I just feel long-term wise, the benefit or the improvement you bring in by doing this is going to be eroded, erased by, the huge data, simple model. That's my belief, But we need to get there step by step. Yeah. And personally, I don't feel explainable AI is that needed here. They actually, I know it's important because science we want to know why, but we will leave this to scientists. Continue those human understandable knowledge will be accumulated by human scientists. But we should not limit AI, to have that capability. That capability is needed by human, but probably not necessarily needed by AI itself. I just don't want that to constrain the development of AI. By the way, if you want to do that, because in Tsinghua, there's also professor always say, we need to make sure AI can explainable. Then they mix big model, they mix large language model, they completely miss ChatGPT. All the recent development, the excitement, they completely miss it because they emphasize it. So I know it's important, but I feel we should not be constrained by that. Doing the when we try to advance the technology. Yeah.
Okay, we have professors from computer science, from material science asking questions. Anybody from chemistry? Okay.
Actually, I'm not from chemistry, but I have a problem is that do we consider the AI as a god? Since now we're just trying to using AI to so many applications listed in the slides, but we do not understand how the model works. So I want to know if the model knows how to generate the context or some prompting or something others, but as human beings, we do not know how they generate these things. Do we have something to do to consider how the model considers this process, and how should we get to know the basic ideas or concepts to know how they works?
Yeah. Yeah, I will try to answer the question if I understand it correctly. Yeah, I feel there's still many limitations of current AI technologies. So that's the reason some people believe current AI and also scaling law is going to lead us to AGI in like 5 to 10 years. I don't buy that. I feel there are still so many things are missing. There are still a lot of important things that we don't have yet. So personally, I don't believe current AI is sufficient to go to AGI. Okay, that's the first thing. And AI for science, even I feel is at the infancy. So that's the reason I feel there are still a lot of opportunity that we can do and to improve. And AI definitely is not God. AI has no free will. Think about we have free will. AI. So that's the reason I feel AI, talking about like a lot of like a threat from AI. AI has no free will. It's controlled, used by human. It's the human need to be the good person, So it's not AI. AI just like is a technology, it's a capability, it's a tool. Yeah. So definitely AI is not God. not even close. I think AI is different from human. I have to say, AI is actually different from human. So this reason, AI is very good at identifying low-level structure from high-dimensional space. Human can only see 4 dimensions. We can see the data correlation. If you present to me in 3D, 4D, I can do classing. But larger than that, think about that. We don't see the pattern easily, right? But AI is good at that. So that's the reason AlphaFold work, because those hidden knowledge can be consumed by AI, but not those structural biologists. They all out of their job. But anyway, I personally feel AI is actually different beast. We need to look at them differently. So yeah, that my whole point is also trying to make. AI is actually good at certain things, but not also good at certain things. And it's not human being, and could be good for natural intelligence. My point is, if we try to solve natural intelligence, maybe AI has something that better than us. So that's the reason some people, if I succeed, I could make a lot of scientists out of job. Think about that. If I succeed in 10 years, a lot of scientists will need to upgrade their knowledge and skill. Think about that. Yeah, so this is why I feel AI first, over AI, by AI, for AI. That's a lot of space to imagine what we can do. Yes.
Anybody from energy? Yeah, you can go ahead and ask a question.
Hi, Professor Ma. I'm not from energy. I'm from economics. Sorry, I will be quick. So my question is about, so what we are doing have limitations on data and on computational power. I wonder which constrains you more, your team more, what you are doing. Because at the background that US is making sanctions and limiting the computing power that can be imported to China. So I'm wondering how much that constrains your research to be the top-notch, cutting edge to the frontier of the world. What do you expect that to limit your capability to be the very front?
Yeah, very good question. I have to say that actually many venture capitalists approach me and my team to start a company as quickly as possible. They will immediately fund us. We are not lacking of money or resource from the VC, but I hesitate. I'm waiting for the perfect timing to create a perfect storm. But not everything are ready, I have to tell you. So this reason I feel we probably need to continue push this in university, because I feel there are many things still need to be developed. So we are actually lack of computing resource, and we are lacking of big data. So scaling law is not completely working in our field yet. Although in the protein large language model, because we have a huge amount of sequence data. The reason why we can do this today is sequence any protein is very cheap. 大华, basically they already technology you can identify the sequence, any protein. So there's a huge amount of data. That's the reason we also want to go from sequence to learn a large language model instead of getting structure, because there are only small amount of structured data. Because it requires certain a special type of equipment to take a picture and really see the ground truth of structure. But that's small data. Yeah, so I think at this moment you just need to find the right problem that has big data, but also interesting problem. There's a need, and we can create value for the problem. You need to have all that to satisfy the requirement of good problem to work on. And but there are not many of them yet. Although I present this exciting space, but each field probably just one good problem to work on now. Even material probably I say will 钙钛矿, because people always talk about you should work on that new material, and could be just we focus on that, right? Biology, protein, right? That's the big things now. Yeah, yeah. So I feel you need to identify the right problem, and there are still window opportunity for the big things to happen. So I would encourage you to just join us, work on this field, and several years from now, I feel there will be tremendous business opportunity for economic growth for Hong Kong as well. I feel But for me, I told you, I'm not ready to hit the button yet. Yeah, because, many things are not there yet. But I predict in the next maybe 2-3 years, 5 years, I think something will come out. You are going to see ChatGPT moment. People, VC always say, when do you predict the ChatGPT moment will appear in our field? I don't know. I don't know. I just feel not yet. But would be.
Yeah, we are almost at the time. So as Professor Ma mentioned, CTU will have deep collaboration with Professor Ma's group. So if you are interested, just let us know, and welcome to join us to join Professor Ma's effort. So now let's thank Professor Ma for the wonderful talk again.
Thank you. Yeah, thank you.
Thank you all. We just finished here.